Hello everyone and welcome to our talk. Today we'll be discussing our ECE6775 project, modeling stateful accelerators in Allo. First, let me outline what we'll be discussing today. An overview of Allo's compilation flow, our motivation and some key applications, implementation details on how we support statefulness in Allo, a demo and our evaluation of the approach, and finally, some pointers for future work. Let's begin with a quick overview. Allo is a Python-embedded DSL, a domain-specific language for describing hardware accelerators. The compilation flow is straightforward. You write the kernel in Allo's Python-based DSL. It is translated into a schedule object, which contains MLIR, a compiler internal representation. Finally, the MLIR is further lowered into VHS-C++ for actual hardware synthesis. Here's what it looks like in code. In this example, we're writing a simple matrix multiplication kernel using Allo's DSL. You can see that the types are imported, and the kernel is described using grid and reduction, a bit like Python with NumPy, but meant for hardware. Allo then translates this high-level DSL into MLIR, a compiler internal representation. As you can see, every loop and memory access is lowered into an explicit typed intermediate representation, making low-level optimizations and hardware mapping possible. Ultimately, this is further lowered into VHS-C++, with HOS-specific pragmas and APIs, representing what will become the hardware logic. So to recap, the Allo compiler moves from high-level Allo DSL to MLIR, and finally to VHS-C++. Let's dive deeper on how we go from Allo DSL to MLIR. This process involves type inference, where we infer the types and shapes of all the variables, as well as MLIR lowering, where we lower the abstract syntax tree into MLIR. We use a few main classes to achieve this: AST context to represent global context, type inferer for type tracking, as well as AST transformer for lowering the abstract syntax tree. From the MLIR, we then optimize and transform the code. We decompose and optimize functions, run several MLIR transformation passes, and finally emit VHS-C++ code from MLIR.
Well, thanks, Tiffany. My name is Joseph, and we'll dive into the motivation of our project. Our problem is Allo is stateless. As we saw earlier, Allo excels at modeling hardware modularly, but it lacks persistent state. Now, the limitation is like drivers cannot assume data persists across kernel invocation, which leads to Allo being less expressive in modeling accumulators, register, or complex ASIC. For instance, partial sum accumulation in general matrix multiplication. Our solution is to have a stateful type qualifier to Allo. This allows us to bridge the gap between high-level Python logic and practical ASIC implementation. Now, with the stateful type qualifier, we're able to add like local scope to our variables, but with global lifetime, very similar to C-style static variables. As a proof of concept, we define like stateless and stateful more formally. By stateless, we mean like a variable which resets at every call, so therefore context is lost. Whereas for the stateful variable, the variable returns its value across kernel invocation, so it behaves much like a hardware register. As we can see in this example, where for the status kernel we're doing accumulation, and then we're passing hex as an argument to accumulate. Across each kernel, this accumulator is always resetted. Whereas like for the stateful kernel, we're able to return value and then like do accumulation effectively. So our key feature is like to add a stateful annotation to Allo types, like integers and all the existing types, even arrays, to mark persistence. We're also able to initialize them with compile time constants. Now, moving on for some real-world applications, as I mentioned for GEM accelerators. So the first use case could be tile matrix multiplication, where the challenge is like for large matrices, they should be like broken into tiles for the hardware. And now the requirement is accumulators must store partial sum to accumulate them over iteration of tile dimensions. So in this example, there is a dot chunk operator. The chunk could be 32-bit or 32 element or 64. And there the driver is using that dot product of 32 or 64 elements, and it's able to resume accumulation after for every chunk. Other applications could be auto like gem accelerator, where we're multiplying like every column by every row to give us a whole matrix, and we will need to accumulate those matrices through iterations. And it's much easier with the stateful type qualifier. How do we do this? So first we need to add the stateful qualifier to our DSL and then to lower its MLIR. So therefore, for type definition, we modify types in the inflorescence file. So we're adding like a marker to flag the type instance, where the only constraint is we cannot have stateful variables as function arguments, very similar to static variables in C, so they can be internal globals. And in the MLR generation stage, we need global storage. There is the memref valid that we're using, and with the memref global, we can generate global at the model level. Now, inside the function, we need local access. We need pointers to those global variables, and we can get them like with the memref get global function. We also support like encapsulation with name angling, which allows us to prevent collision and also to be able to add isolation of states.
This slide describes how we implemented the MLIR to VHLS lowering with a focus on supporting both the stateless and stateful execution models as required by the Allo dialect. VHLS already supports C-style static semantics, meaning a variable marked static persists across kernel calls and hardware. We leverage this by translating any MLIR variable marked with an HLS.static attribute or the stateful naming pattern into a static declaration in the generated VHLS code. The VHLS generation pass implemented in the emit vivato HLS C++ file performs 4 key tasks. Detection, where we identify stateful variables based on MLIR IR attributes. Emission, where these stateful globals are then lowered to function local static variables in the generated C++. Initialization, where we emit the proper type qualifiers, constants, and initial values and handle arrays correctly. And deduplication, which is a per function pass that collects references to prevent redundant emission. This gives us consistent state behavior in hardware and makes stateless versus stateful lowering fully automatic inside the compiler. Now we will move on to the demo. To demonstrate the functionality of the stateful attribute in Allo, we have 2 examples of scalar accumulators, one that is stateless and one that is stateful. And the stateless accumulator example implementation can be seen above in the Python code. We will run both files and generate the corresponding C++ code and see the differences. So for the stateless accumulator, we can see that there is no static variable generated in the HLS code as seen in the terminal. And then for the stateful accumulator example, this is the Python code. And once we generate the C++ code with this file, we can see that by using the stateful attribute, we actually generate a static variable to maintain state. For the purposes of this demonstration, we have already built the necessary host and kernel files using the generated C++ code from the stateful scalar accumulator example as seen previously. And we're going to run this on the FPGA to show the full functionality and to verify the expected results. So we'll add an input value of 50 and reset the accumulator by setting that Boolean value to 1. And as we can see, the execution is as expected with the accumulation value of 50 incrementing over 5 iterations after having been reset. And in the host file, we can see that for each iteration, the stateful accumulator kernel is invoked multiple times, which correctly demonstrates that the generated C++ code is able to maintain and preserve state.
Thank you for the great demo. Hey, I'm Sonu, and I'll conclude our talk with evaluation and future works. Here we present the performance aspect of the previous example. To implement the same functionality using stateless Allo, we had to keep the intermediate results at host. This involves additional memory copy between host and accelerator hardware, which is about 20% in total runtime, as shown in the table here. This advantage shows that users can implement more realistic accelerator scenarios where they can invoke kernels multiple times, now in Allo. For future work, first, we are implementing more realistic accelerator with on-chip scratchpad as a stateful variable. This will demonstrate the Allo can be used to model realistic and extensible accelerator designs. Also, we plan to improve the driver and user interface. As original Allo was not meant to be invoked multiple times, this improvement is necessary. Next, we plan to exploit the Vitis HLS functionality of specifying VRAM IPs. We believe this will open optimizations for larger scale designs. To conclude, we implemented a new state feature in Allo, which enables users to model states that persist across invocations. We believe this enables the Allo ecosystem to model more realistic and extensible accelerator design, and we demonstrated its usefulness using an integer accumulator example. As we are pushing our contribution to the Allo upstream, please stay tuned. Thank you for listening.